Hi everyone, welcome to Additive Combinatorics. In this lecture we will return to a central topic of this course, subsets of abelian groups without three-term arithmetic progressions. We've considered two extremes. On the one hand, the cyclic group of order n with n very large, and on the other hand, the additive group underlying a high-dimensional vector space over a fixed finite field. Using Fourier analysis we obtained comparable upper bounds in the two situations. For the lower bounds, the situation was quite different. In the finite field case, the lower bounds are much farther away from the Fourier upper bounds. So a natural question in the finite field case is therefore whether the lower bounds are very far from optimal, or perhaps the Fourier bounds are just very poor. And this is essentially what the CAPSET problem is about. Now the CAPSET problem was resolved in 2016 in two subsequent papers. The first paper was by Kroot, Leff and Pach, and the second paper was by Ellenberg and Gijswijk. The solution uses techniques that are very different from Fourier analysis and belong to a growing set of ideas that are collectively referred to as the polynomial methods. In this lecture we will explain the CAPSET problem and the methods used to solve it.
Throughout this lecture, P will be an odd prime. A subset A of the n-dimensional space over the field of P elements is called 3AP free if it doesn't contain any proper three-term arithmetic progressions. A closely related concept studied in affine geometry is that of an affine cap. A subset A of the n-dimensional space is called an affine cap if it doesn't contain 3 points on a line. The first non-trivial case, and also the most studied case, is when P is equal to 3. For P is 3, a 3AP3 set is the same as an affine cap. Indeed, every line contains exactly 3 points. In this case, an affine cap or 3AP3 set is often referred to as a cap set. Also for P bigger than 3, we will refer to a 3AP3 set as a cap set, simply because it's much easier to pronounce. We will refer to the maximum size of a cap set in dimension n as AP of n. For P is equal to 3, some exact values are known, namely for dimensions 1 up to 6. Already dimension 7 is unknown. Of course, dimension 4 corresponds to the famous card game set. 20, the maximum size of a cap set in dimension 4, corresponds to the maximum number of cards you can have without any set. In the previous lectures we've seen asymptotic upper and lower bounds. The upper bound of Meshulam used Fourier analysis. It is comparable to Ross's bound in the case of Z mod nz. Meshulam would translate into n over log n. This is not quite the bound we got in Ross's theorem. However, it is very close to the current record by Bloom, which refines Roth and gives n over log n times the power of log n. The lower bound of Bierbrauer that we saw in the last lecture is quite far away from the upper bound. The analogous bound for the case of Z mod nz would be n to the power 2/3. Which is much lower than what we get from Beeren's construction. In the case P is 3, the best known lower bound is due to Adel. Like other lower bounds, it uses the product construction applied to a cap in fixed dimension, in this case in dimension 480. The upper bound was improved by Bateman and Katz. In the denominator, the factor n was improved to n to the power 1 plus epsilon, for a very small epsilon. The result was quite surprising, as the analog bound for Z mod nz would break the log n barrier. The upper and lower bounds on cap sets are very far apart and qualitatively different. So the question is, which type of bound is the correct one? The cap set problem suggests that actually the lower bound is close to the truth, in the sense that the density of cap sets decreases exponentially with the dimension. More precisely, the cap set problem asks, is the maximum size of a cap set at most on the order of c to the n for some constant c smaller than a prime p? In this lecture we will show that the answer is yes. This theorem is based on earlier work of Krutlev and Pach. They showed a similar result for 3 AP3 sets in Z mod 4Z to the n. Their main lemma is one of the key ingredients in the solution of the cap set problem. The proof of our main theorem uses several ideas from the polynomial method. The first is the classical linear algebra method, or rank method. The idea is to map your combinatorial objects into a linear space in such a way that a dimension counting argument gives the required upper bound. We will illustrate this using the famous story of even town and odd town. Even town is a town with n people. The inhabitants of even town really like to form clubs, as many as possible. There are some rules, however. First of all, every club must have an even number of members. Secondly, different clubs must always have an even number of members in common. Finally, no two clubs are allowed to have exactly the same members. Okay, so now the question is, what is the maximum number of clubs that the people of Eventown can create? Remember that they won't shy away from creating the empty club, the club with no members at all. Let's suppose for simplicity that n is an even number. So what we can do is we can pair up the people of Eventown, and then we create clubs that consist of whole pairs. It's now easy to see that in fact we can create at least 2 to the power n over 2 clubs. Since all clubs in Eventown have to be officially registered, the mayor of Eventown is not really happy with this situation. The rule that every club must have an even number of members is changed so that now every club must have an odd number of members. From now on, the town will be called Odd Town. Again, we can ask, what is the maximum number of clubs that the people from Odd Town can form? Well, they surely can form at least n clubs, because they can make every person into a single club, all by their own. Now, the interesting fact is that n clubs is in fact optimal. It's not possible to get more than n clubs. To show this, we will use the linear algebra method. Okay, let's have a look at the proof. We start by defining a 2 to the n by 2 to the n matrix M. The rows and the columns of the matrix M will be indexed by all subsets of the set of elements from 1 to n. For row A and column B, we define the corresponding entry of the matrix to be the number of common elements of A and B modulo 2. The first thing we observe is that the rank of M is at most n. Indeed, consider the matrix L, whose rows are indexed by the subsets of 1 to n, and whose columns are indexed by the elements of 1 to n. Every row of the matrix L is just the 0,1 incidence matrix of the corresponding subset. It's now easy to see that the matrix M is just L times L transpose. Now, since the number of columns of L is only n, that means that the rank of L is at most n. But then also the rank of M is at most n. Now let's consider our collection C of clubs. Now look at the submatrix of M indexed by the rows and columns that are in the collection C. This submatrix is the identity matrix. Indeed, consider any two clubs in C. If they are the same club, then because all clubs have an odd number of members, the corresponding diagonal entry must be 1. On the other hand, if the two clubs are different, then they share an even number of members, so the corresponding entry in the matrix is 0. But this implies that the rank of the matrix M is at least the size of C, at least the number of clubs. So this concludes the proof. To prove our main theorem, we'll be working with polynomials in n variables over the field of p elements. By x to the power alpha, we mean the monomial, where variable xi has exponent alpha I. By absolute value of alpha, we mean the sum of the components of alpha. So that is the degree of the monomial x to the power alpha. Given a polynomial in n variables, we can of course view it as a function of n variables by substituting values for the variables. But since we're working modulo p, the polynomials xi to the p and xi, they represent the same function by Fermat's-Little theorem. So from now on, we'll only consider polynomials in which no variable occurs with exponent more than p minus 1. This way, no two polynomials represent the same function. It turns out that conversely, we can represent every function by a polynomial. We'll leave the proof as an exercise. By MD, we denote a set of monomials of degree at most d. Again, we only consider monomials in which each variable occurs with exponent at most p minus 1. For convenience, we allow d to be any real number, not necessarily an integer. By little md, we denote the number of elements of big M, d. So this is the dimension of the space of polynomials of degree at most d, viewed as functions. Given a polynomial in 2n variables, we can view it as a matrix. The columns and the rows of the matrix are indexed by all elements of fp to the n. Given two n tuples a and b, we obtain the corresponding entry in the matrix by substituting a for the first n variables and substituting b for the second n variables. This way we obtain a linear map from the set of all polynomials in 2n variables, again with the restriction that every variable occurs with exponent at most p minus 1, to the set of all p to the n by p to the n matrices. In fact, this map is a bijection. An important special case is where a polynomial in 2n variables is actually a product of a polynomial in the first n variables and a polynomial in the other variables. In this case, all the rows of the matrix are scalar multiples of each other. In other words, the matrix has rank 1. This will be important in the proof later on. We now come to the key lemma of Kruglev and Pach. The statement of the lemma is as follows. We let A be a subset of the n-dimensional space over Fp, and we let f be a polynomial in n variables of degree at most d. Now suppose that for any two elements a and b in the set A, f of a plus b is 0 if and only if a and b are distinct. The claim is that the cardinality of A can then be bounded in terms of the degree d. It is at most 2 times the number of monomials of degree at most d over 2. Let's take a look at the proof. The main idea is that given a polynomial p in 2n variables, we can bound the rank of the corresponding matrix in terms of the degree of p. To start, we define a polynomial p in two n variables by saying p of x comma y is f of x plus y. To p we associate a matrix MP as before. Note that the submatrix indexed by the elements of A is a diagonal matrix with non-zero elements on the diagonal. This is because f of A plus B is equal to 0 if and only if A is not equal to B. From this we conclude that the rank of the matrix MP is greater or equal the number of elements in A. The next step in the proof will be to upper bound the rank of MP. Okay, let's write P as a sum of monomials x to the alpha, y to the beta. Since the degree of P is at most d, this means that the absolute value of alpha plus beta is at most d for every monomial occurring in the decomposition. This means that in any monomial, either the absolute value of alpha is at most d over 2, or the absolute value of beta is at most d over 2. So in this way we can sort the monomials in two groups, the ones where the x variables have total degree at most d over 2, and the monomials where the y variables have total degree at most d over 2. The monomials for which both the x variables and the y variables have total degree at most d over 2 can be put on either side. In the resulting decomposition, each term is a polynomial that's the product of a polynomial in the x variables and a polynomial in the y variables. Hence, the corresponding matrix has rank at most 1. Counting the number of terms in the decomposition, we find that NP is the sum of 2 times MD over 2 rank 1 matrices. Hence, MP itself has rank at most 2 times MD over 2. Combining this upper bound on the rank of MP with the fact that the rank of MP itself upper bounds the size of A concludes the proof. Okay, we're now ready to prove the main theorem. Let P be an odd prime. We'll prove that the maximum size of a cap set is bounded by 3 times Cp to the n, where Cp is a constant strictly smaller than P. The proof will consist of two parts. In the first part we'll upper bound the maximum size of a cap set by 3 times the number of monomials of degree at most p minus 1 n over 3. In the second part we'll bound this number of monomials by Cp to the n for some constant Cp strictly smaller than P. First we'll need a small lemma. Let V be a d-dimensional subspace of Fp to the n. Then there is an element in this subspace whose support has size at least d. By the support of a vector we mean the number of components that are non-zero. The proof essentially boils down to Gaussian elimination. We are now ready to give the proof of the main theorem. Let A be a subset of Fp to the n without 3-term arithmetic progressions. We would like to use the Crude-Left-Bach lemma to upper bound the size of A. For this we would need a polynomial f with the following two properties. First of all, for A and B in the set A, we need f of A plus B to be 0 if and only if A and B are distinct. Secondly, we need the degree of f to be sufficiently low. It turns out that we cannot quite achieve this. It turns out that this is a little bit too much to ask. We cannot achieve this, so we will need to tweak the argument a little bit. Let V be the set of polynomials of degree at most d that vanish outside of the set 2a. The degree d will be chosen later. Let f in V have maximal support. That is, the set of points where f vanishes is as small as possible. We denote by A' the set of elements in A for which f of a plus a is non-zero. In other words, 2a' is precisely the support of f. See the diagram on the right. Ideally, we would like a' to be equal to a. Although this is not the case, we can bound the difference in size. The size of a' equals the size of the support of f. So, by the lemma, this is at least the dimension of V. The dimension of V is at least the dimension of the space of polynomials of degree at most d, minus the number of linear equations we imposed. What we find is that the size of a' is at least the size of A minus p to the n plus md. Now consider any two elements A and C of the set A'. If A is equal to C, then f of A plus C is non-zero by definition of A'. If A and C are distinct, then A plus C cannot be in 2A, since A has no arithmetic progressions. So in that case, f of A plus C must be 0. Since f had degree at most d, it now follows from the Kruglev-Bach lemma that the size of A' is at most 2 times m d over 2. Combining the two inequalities for A', we get an upper bound on the size of A. A is at most 2 times md over 2 minus md plus p to the n. The degrees of monomials range from 0 to p minus 1n. The number of monomials of a given degree is symmetric around the middle, the total count being p to the n. The fraction of monomials of a given degree follows the multinomial distribution. It models the probability of counts for a p-sided dice. By symmetry, the two blue areas in the figure are the same. If the right-hand area corresponds to the monomials of degree bigger than d, the left-hand area corresponds to the monomials of degree less than p minus 1n minus d. Hence, we obtain the following inequality. If we now choose d to be 2/3 times p minus 1 times n, we obtain the desired bound. To complete the proof of the main theorem, we have to estimate the number of monomials of degree at most p minus 1n over 3. To this end, we define the following function phi. We let Cp be the minimum of the function phi on the half-open interval 0, 1. Here you see a plot of the function phi in the case that p is equal to 3. We now claim that the number of monomials of degree at most p minus 1n over 3 is at most Cp to the power n. Okay, let's look at the proof. We define the function f to be the nth power of the sum of 1, t squared and so on up to t to the power p minus 1. Expanding f, we see that the coefficients exactly count the number of monomials x to the power alpha of a given degree. Using the fact that t is at most 1 and positive, the required estimate easily follows. The final piece of the puzzle is to show that CP is strictly smaller than P. To show this, first observe that the function phi is differentiable on R+. Since phi of 1 is equal to P, and the derivative of phi in 1 is positive, this immediately implies that the minimum of phi between 0 and 1 is smaller than P. In the case that P is equal to 3, we can compute the minimum by setting the derivative of phi equal to 0. This gives a second degree equation, and solving it gives us a value of C3 around 2.755. This concludes the proof of our main theorem.